There's a fun little fact that comes into play when we're talking about whether or not two events are causally connected in space-time. Let me describe it to you. It's the following fact. So if you have 2 points that are causally connected, the invariant interval between them is negative, then the claim is there is a frame of reference such that those 2 events happen at the same place in that new frame of reference if its velocity is chosen correctly. And if 2 events in space-time are causally disconnected, if they're space-like separated, the claim is there is a frame of reference in which those 2 events happen at the same time. In the boundary case, we say that they will lie on a causal boundary, and we'll describe what that means in a moment as well. But let me try to establish this fact for you, and it's easy for us to do. So let's set up a new space-time coordinate system here. So here we'll say be our t-axis. This will be our x-axis of our initial system. And let's choose one of our events to be at the origin to keep life simple. And let's look at another event with which there is a causal link because the invariant interval will be negative. And let's figure out what frame of reference it would be in which these 2 events, as we see, happen at the same place. How can we do that? Well, it's pretty clear what we do. Here is that frame of reference. Let me draw it in red. So this will be my new t prime axis passing through those 2 points. And this will be my new x prime axis, chosen again so that its angle relative to x is the same angle of t prime to t. So let me now mark these guys. So if I take this to be x prime, this to be t prime, this is a single location in space over many moments in time. So from the perspective of the red frame, this white dot and this white dot, this event and this event are happening at the same place. They're happening at the origin in this coordinate system, but they are happening at different moments in time. Now, is this a sensible trajectory? Can that actually be achieved? Of course, because the very fact that these points were causally connected means that a signal can go from here to here at a speed slower than the speed of light. And all we're doing is we are riding along with that signal in this particular frame of reference. So in the example where Gracie was throwing the ball at George, imagine you go into a frame of reference where you are moving with the baseball. From your perspective, Gracie throwing the ball and the ball hitting George in the eye, those are happening at the same place in your frame of reference, and here is that frame of reference. For the other case, if we are looking at events that are space-like separated, let's do that over here. Let me choose another point for a space-like separated event. Let's choose one, say, at this location. The origin and that point are space-like separated. No way for a signal to go between them, but the claim is there is a reference frame where those 2 events happen at the same time. What is that reference frame? Well, I'll draw it for you. So let's choose another color so we can keep this straight. So I'm going to choose my new x double prime axis. Let me see if I can get this to go through. Hey, that's not too bad. So that will be my x double prime axis. What about my t double prime axis? I just choose the same angle over here. So that guy comes down. Yeah, it's not perfect, but pretty close. Let me mark those to keep them clear. So this guy will be x double prime. This guy will be t double prime. And in the green system, these 2 space-like separated points are happening, as you see right over here, they're happening at the same moment in time, right? Different locations in space, same moment in time. That, in fact, is t double prime equal to 0. It's the origin in time from the green frame's perspective. So there you have it. You can immediately write down frames of reference that establish the claim. If you like to do things algebraically, you of course can do that too. So if you want to write down the equation, for instance, in this particular case over here, where we wanted this point and this point to happen at the same location, the equation you would solve, therefore, is delta x prime equal to 0. Now that, of course, is gamma times delta x minus v delta t. Setting that equal to 0, you simply have delta x equals v delta t, and it's just obviously giving you that the velocity of this frame, you choose it to be the spatial separation between this point and this point in the original frame divided by the temporal separation. But that's just saying what I said before. You're moving along with the baseball, and in that frame, the two events are happening at the same location but at different moments in time. You can play the same game for the space-like separated ones, but I encourage you to do it, but you'll see that it works out just the same. So the nice thing here is we have a nice picture of what it means for events to be time-like or space-like separated. So they are time-like separated if there is a frame of reference in which the only thing that separates them is time. They are space-like separated if there exists a frame where the only thing that separates them is space. That's where the language comes from. This also gives us a nice physical interpretation of what the invariant interval is, because in the case where there is a causal connection, what is the meaning physically of the invariant interval minus c delta t squared plus delta x squared? Well, look, in this frame, delta x prime is equal to 0. So if we plug that in to this expression, delta x prime equal to 0, tells us that the invariant interval is nothing but minus c delta t prime squared. And that is something that obviously we can interpret. That's minus c squared times the time in this frame between the events. So you can think about the invariant interval in that case as minus c squared times the amount of time that elapses on a clock that is moving with the signal from one person to the other, from the cause to the effect. So going back to Gracie and the baseball, baseball is traveling along. If we travel with it, then from our perspective, the ball is at one fixed spot. We look at our watch between when Gracie throws it and when it hits George in the eye. That amount of time, delta t prime, multiply it by minus c squared, that is the meaning of the invariant interval. So you can think about the invariant interval between two causally connected points as minus c squared times what we call the proper time, the amount of time that elapses on a clock for which these two events are taking place at the same location in space. Good. What about the other case? Oh, and I should say, point of notation, we often introduce the symbol tau. I'll come back to this later, which is why I'm mentioning it now. We often call tau the proper time to distinguish it from the laboratory time, which we often use t. So the amount of time that elapses on a clock that is traveling along with the signal from one event to the other is the proper time between those two events. What about the other case? If they are causally disconnected, what then is the meaning of the invariant interval? Well, it's pretty clear, right? So what is the meaning of minus c squared delta t double prime squared plus delta x double prime squared? Well, look, the invariant interval between these guys, minus c squared delta t double prime squared plus delta x double prime squared. This now is equal to 0 in that frame of reference. So all we get, therefore, is delta x double prime squared. So the invariant interval between this point and this point is nothing but the distance between them measured in a frame of reference where those events happen at the same moment in time. So that we call the proper distance between the two events. And that is the way in which you should think about the invariant interval. When there's a causal link, it's the proper time between the events. When they are disconnected, no causal link, it is the proper distance in space between the events.